You know, when you look at some of the most complex systems imaginable, we're talking everything from vibrating bridges to how facial recognition software works. They often have these simple, hidden rules kind of running the show. And today, in this explainer, we're going to uncover one of the most powerful of them all. All right, let's dive right in. I want you to picture something called a linear transformation. It sounds complicated, but it's really just a rule that takes a vector and spits out a new one, usually by stretching it, shrinking it, or twisting it around.
A perfect way to see this in action is with something called a shear. Think about taking a square picture. Now imagine you hold the bottom steady and just push the top of it to the right. It's kind of like skewing a deck of cards, right? Almost every single point in that picture gets shifted and tilted away from where it started.
But here's where things get really interesting. While almost every vector gets knocked off its original line, a few special ones don't. They hold their ground. Look right there along that central horizontal line. Any vector on that line just gets stretched out. It doesn't turn one bit. It stays pointed in the exact same direction. So that's the big mystery we're here to solve. In this whole chaotic world of twisting and turning, why do these stubborn vectors even exist? What gives them this special property of being immune to the rotation? Well, as you might have guessed, these special vectors have a name. And they're not just some quirky math oddity. They're called eigenvectors, and they are absolutely fundamental to understanding what a linear system is really doing under the hood. So let's get the formal definition on the table. An eigenvector is any vector, as long as it's not the zero vector, that when you apply a transformation to it, stays on the very same line it started on. That's it. You can kind of think of them as the true axes of the transformation itself. And every eigenvector has a partner in crime, its eigenvalue. The eigenvalue is just a number, and it tells us how much the eigenvector got scaled. Did it get twice as long? Boom, the eigenvalue is 2. Did it get cut in half? The eigenvalue is 0.5. It can even flip and point the other way. That just means it has a negative eigenvalue. And this is the beauty of it. This entire, incredible relationship is captured in one simple, elegant equation. On the left, you've got the complex transformation A acting on the vector V. But the equation tells us that's the exact same thing as just taking that vector V and scaling it by a simple number, its eigenvalue, lambda. And that name, eigen, is just perfect. It comes from the German word for own, because these vectors are truly intrinsic to the transformation. They're not random. They define its own unique character, its fundamental directions of action. Okay, so that's what they are. But how in the world do you actually find them for any given transformation? Well, it turns out there's this incredibly clever piece of logic. It's like a treasure map that leads us right to them. Let's check it out. Okay, let's walk through this because the logic is just brilliant. We start with our main equation. Now, with a little bit of algebra, we can shuffle things around to get everything on one side. That I you see there, that's just the identity matrix. You can think of it as the matrix version of the number 1. So now we have this new matrix A minus lambda I that when we multiply it by our eigenvector V gives us nothing, the 0 vector. Now we already know that V, our eigenvector, can't be 0. So for this whole thing to work, there has to be something special about that matrix part. It has to be what we call non-invertible. It's a matrix that squishes space down into a lower dimension, like from a plane down to a line. And that leads us to the final, crucial leap. The one thing we know for sure about these special non-invertible matrices is that their determinant, a number that tells you how much they scale space, is always, always 0. And just like that, we have our treasure map. This is the characteristic equation. All we have to do is solve this for lambda, and it will spit out the exact, unique eigenvalues for our system. Now, I know this might all seem a little abstract, like we're just solving math puzzles. But trust me, finding these own vectors, well, it lets us solve some of the most incredibly complex and important problems in the real world. Seriously, the applications are mind-boggling, and they pop up in places you would never expect. Engineers use them to find the natural vibrating frequencies of a bridge so they can make sure it doesn't collapse. In computer science, the famous Eigenfaces algorithm was a key breakthrough in facial recognition. They are absolutely critical in quantum mechanics, where the Schrödinger equation uses them to define energy states. They're used to predict the long-term future of systems. And today, in data science, a technique called principal component analysis uses eigenvectors to find the most important patterns hidden inside mountains of data. And here's a really crucial takeaway. In a lot of these dynamic systems, like say a model of a population or the stock market, there's usually one eigenvector that ends up being the most important. It's the one with the biggest eigenvalue, often called the principal eigenvector. And over time, it's this one direction that basically dictates where the whole system is going to end up. It points the way to the system's most stable long-term state.
So, after all that, when you boil it all down, what's the one big idea you should really take away from all this? It's this. They reveal the hidden skeleton of a system. They are the stable axes that all the complicated, messy dynamics revolve around. So no matter how chaotic things might look on the surface, if you can find these special directions, you can understand the entire system in a much simpler, more profound way. It really makes you wonder, doesn't it? If you just look for the things that don't change direction in the middle of all the chaos, you can often understand the true nature of everything else. So the question is, what hidden structures, what eigenvectors are shaping the complex systems that are all around us right now?